In this short presentation, we will provide some, we hope, useful insight on different educational resources which may be employed for integrating a systems thinking approach to teach topics of applied chemistry. More specifically, we will make reference to 5 practical examples that have appeared in the recent research literature in the field of chemistry education. Redesigning and reimagination of learning, teaching, and research to achieve the goal of making chemistry green and sustainable is highly desirable. To do so, chemists must orient their efforts toward the implementation of scientific knowledge into useful applications by encouraging collaborative interdisciplinary work to meet the emergent challenges of global crisis. Systems thinking is recommended for reimagining chemistry education because it helps in the development of an integrated and sustainable approach that takes into account the interdependence of a system understanding with other components of the ecosystem rather than practicing a fragmented approach. Systems thinking also describes the life cycle analysis of a commercial product, starting from the origin of its feedstock to its manufacturing process and finally its use, reuse, and disposal. In addition, systems thinking stimulates intellectual reasoning related to a product's impact on society, humankind, economy, and natural environment during its entire lifespan. A characteristic application of systems thinking related to drug design and development was proposed in this first example, which is based on this work of Holm, published in 2020. This example, on one hand, introduces the fundamental concepts of life cycle analysis, particularly as applied to pharmaceuticals, and on the other, it makes use of an organizational scheme to help visualize the connections between subsystems for the design, development, and production of the drug substance cytarabine, which may be used for the treatment of childhood leukemia. This organizational scheme is known as a systems-oriented content map extension diagram, or in short, a SOCMI diagram. The layout of the SOCMI diagram for the drug substance cytarabine is shown in this figure. The interconnectedness of 7 different subsystems, namely the core chemical theories, the mimic, the discovery, the biochemistry, the side effects, the economics, and the ethics subsystems is nicely portrayed in this figure. Moving on to the example presented in this recent work of Sharma and co-workers, a green chemistry laboratory experiment has been designed to give students an introduction and a hands-on experience to nanotechnology through nanoparticle synthesis and presents practical applications of nanotechnology in wastewater treatment. It also aims to developing students' ability to adapt and react to the growing global challenges, such as those mentioned in the United Nations Sustainable Development Goals, in a more responsible and sustainable manner. Specifically, magnetic nanoparticles, MNPs, are synthesized using plant-derived potato extract and following ethical rules and sustainable principles such as use of efficient, cost-effective, safe, and clean raw materials and use of plant-derived reducing agent. Additionally, the synthesized MNPs are utilized for treating wastewater containing rhodamine B as a model organic pollutant. Further, the recyclability of MNPs was tested in successive runs. The experiment described in this second example is proposed to promote the development of students' higher-order thinking skills, known as HOTS, based on the enactment of a systems thinking hierarchical learning model. This model includes the build-up of 3 levels visualized in this figure that take note of the desired and possible impacts of methods and products at every stage, starting from the sourcing of reactants to the final step of recycling. Moving on to another interesting applied chemistry topic, we turn our attention to the work of De Kemper and co-workers regarding sustainable lighting. In fact, light-emitting diodes, LEDs, seem to be the most sustainable light source of the future because of their high power efficiency and longer life cycles. One of the most important materials for wide-emitting LEDs is cerium-doped yttrium aluminum garlet, YAG cerium, the most widely used luminescent material in wide LEDs. A school and student-friendly synthesis of YAG cerium in a laboratory microwave oven aims to demonstrate chemistry's contribution to sustainable development in a comprehensible way via teaching the students to take a critical and holistic perspective with a view to a changed, more comprehensive and more critical assessment of the advantages and disadvantages, as well as the opportunities and possible risks of LED technology. Moreover, it stimulates critical questioning about raw materials, their production, their life cycle, and potential recycling processes. This figure tries to provide a visual representation of how this third example of applied chemistry promotes students' system thinking ability by showing how the different phases of the educational experience bring out the interconnectedness between different science disciplines, chemistry, physics, with the elements of policy, economics, and society within the Earth system. In this fourth characteristic example, based on the recent work of Zwin and co-workers, the enormous amount of waste generated locally by the citrus processing industry was used as a case study for a guided inquiry laboratory experiment that addresses concepts found in interfaces with other systems, such as biorefineries, biocircular economies, green technologies, and professional education programs. Additionally, a set of green and sustainable chemistry education principles composing a new metric called the Green and Sustainable Chemistry Education Compass Rose was proposed that could help educators develop and assess novel experiments to modernize and introduce the scientific concepts and tools needed to face the world's greatest challenges. Waste valorization may be described as the process of converting waste, for example via reusing, recycling, or composting, to useful products or energy sources. In this work of Jefferson and co-workers, a demonstration was developed to introduce students to waste valorization, converting sour milk into a bioplastic via the addition of lemon juice upon heating. The use of lemon juice as a green alternative to the use of the chemical formaldehyde employed traditionally in the chemical industry enables students to identify links with different United Nations Sustainable Development Goals. These goals are specifically goal number 4, quality education, number 9, industry innovation and infrastructure, number 11, sustainable cities and communities, number 12, responsible consumption and production, number 13, climate action, number 14, life below water, and number 15, life on land. However, as brought out in this example, the valorization process for converting sour milk into a bioplastic that may be used as a decoration material may also be employed for the production of paneer, a non-melting farmer cheese used as an important source of food to provide nutrition and alleviate hunger in parts of India and elsewhere. As such, this provides an additional opportunity to demonstrate to students that valorization of sour milk in this way also serves to address goal number 2 of the UN SDGs pertaining to the end of hunger, achievement of food security and improved nutrition together with promoting sustainable agriculture. In this way, students are also exposed to the other side of the coin, the one related with the ethical implications of making bioplastics from milk, and they are urged to engage in a mental process based on the systems thinking approach. Reaching the end of this short lecture, we may conclude that as depicted via the presentation of these 5 characteristic cases, the integration of systems thinking within a variety of themes related to applied chemistry may act as a potent driver for chemistry education towards new directions, which will serve the very much needed and urgent goals of sustainable development. Thank you.